Hi, my name is Zhi Qian, and now I will demo how the half adder works. So we first construct the schematic diagram of the half adder in quarters, and then we compile it. After we compile it, if no errors, we will go to File and New. We open the University Program PWF. So in here, we start to insert the node in our schematic diagram, and then we will set end time and the input value for our inputs. So 0, 0, 0, 1, 1, 0 and 1, 1. So we will start to simulate it. If there is no error in our input, then here is the output. So if it just add the input together and get the output. So as we can see here, when 0 and 1, it gives out 1 at the output and 0 carry. If 1, 1 in the input, it gives out the output is 0 but the carry is 1. So for the second part is the full adder. So when we need to construct the full adder, we need to import the half adder from the last part, the simple file, and then we just connect it as in the milestone. So after we construct it, we can click the compile, and that is the report. If there are no errors, we can proceed it to the waveform. So in here, same as the part 1, we just insert the node. After we insert the node, we insert the value in as shown in the Milestone 1. So it's 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, and etc. So start simulate it. This is the result. So it's same like the half adder. It just add the 3 bits together and produce the output. Example for this, 0, 1, 1, and it produce out the output is 0 but the carry is 1. So for the part 3, the ripple carry adder, we need the full adder simple file from the part 2, and then we construct the schematic diagram as in the Milestone 1. Then we compile it, and this is the report, and there is no errors, so we can proceed it to the waveform file. So the step is like part 1 and part 2. So I group all the inputs into one bus, and output B into bus B, and then output S into bus S. Then the end time is 1000 nanoseconds, and the input is key in from the test data in the Milestone. So we can start stimulate it. As this is the result, and the slightly difference we can see is at this part, where the input is 8 hexadecimal and B also is 8. So it will provide out 0 output at the S but 1 at the C output. So it's this part.
Hi, I'm Xiang Yu. So I'll be doing the 1.2, which is bus multiplexer. So first I will be doing the 1.2.1, which is the 2 to 1 multiplexer. So first of all, we need to open a new project and we'll place the component in the block diagram, which is given in the PDF file. So this is the block diagram for the 2 to 1 multiplexer. So AB is the input, S is the selector, and Y is the output. So after that, we'll compile the block diagram and we'll get the compilation report. So after that, we need to simulate the result. So we'll require to put the for all inputs for AB and all four input combination for AB and S. So Y will be the output. So we'll start simulate. So this is the output Y. So for output Y, when the selector is 0, so the output Y will be same as the input A. So it's because from the block diagram we can see uh, S when S is 0, so this is the NOT gate, so here will be 1. So A will produce whenever the input A, it will show the result of the input A. So when the selector is 1, so the Y output will follow according to the input B. So this is the 2 to 1 multiplexer. Okay, so for 1.2.2, we are required to do a 4-bit bus multiplexer. So first we need to create a symbol for the 2 to 1 multiplexer, which is created from here. Create a symbol files for current file. So after that, we place the 2 to 1 multiplexer symbol here and we placed all of the components which are as given. So A and B is the input, S is the selector, and Y is the output. So after that, we'll compile the block diagram and we'll get the compilation report. So after that, we need to simulate the waveform. We need to simulate the inputs which is given. So these are the inputs. So we need to get the output. So we'll simulate. And we get the Y output. So as we can see, the 4-bit bus multiplexer is almost same as the 2 to 1 multiplexer, just as it is 4-bit. So the selector, when the selector is 0, so the output Y will same as the input A, and when the selector S is 1, so it will follow the output Y will follow the input B. So that's it for my part.
For the demo of Milestone 1.3 data register, so first of all, construct the circuit inside quarters according to the schematic diagram provided in the Milestone 1.3. And before you construct this circuit, you have to go to project, add or remove files in project, and these libraries. Under the project libraries, you have to browse and include the Milestone folder, which is Milestone 1.2 that you have done before. So as you can see, I already include the
Milestone 1.2 file folder inside my project. And after you include it, click apply and OK. After including the libraries, you can only find this. Click this symbol and you can enter the Mux 2.1 that required for constructing the circuit. And for my case, my partner saved the Mux 2.1 as Mux 2.1 new. So key in the name and you'll get the block for it, and you can put it here. So after constructing the circuit, you'll click this compile. So you can see the compile progress. Wait for the progress finish. Click File, New, and click this University Program VWF. Okay. And in this blank place, right click, insert node or bus, node finder, this, include all this node, okay, and click OK. So to set the waveform as required for the Milestone project, you click this D out, pull it down here, and click this clock, and select this one, override clock, select the period, and insert 80 nanosecond. Click OK. And for the D in and ID part, you can manually highlight them and click this forcing high, so that they will become the same as the required in the project. After setting the waveform the same as required, click this run functional stimulation and wait for it to stimulate the waveform for output. And as you can see, when the clock is high and the ID is high, the circuit will register the value in the D in into the output, and when the clock is low, it will do nothing for the output until another clock is high input signal and the ID is high input signal. The circuit will again register the value in D in, which is low, into the output. And when the clock is high and ID is low, the circuit will do nothing to the D out. So after verifying the function of the register cell, we can come back to the schematic of the register cell and click File, Create symbol files for current file, and type in the name you want to save. For this case, I will type rec cell and click Save. After you save it, you can find it inside this symbol. When you type in rect cell, you can get the block of the rect cell. And for the milestone 1.3.2 4-bit data register, as the same, you have to go to project, add or remove files in project, get to the libraries, add the related libraries, apply and OK, and you can start design your circuit as shown in the project. So after you design, click this compile and wait for it to run. Wait for this progress. And after the compile finish, as usual, go to File New, and this University Program VWF, OK. Right click, insert node, node finder, list, include all nodes here, and OK. Select the clock, override clock, change the period to 80 nanosecond. OK, and you can highlight this part, right click it. So for this case, highlight 160 until 320 nanosecond, right click, value, arbitrary value, and in this numeric or name value, change to 0111, click OK, and do the same for the rest until you get the required waveform, and click this run functional stimulation and wait for it to stimulate the output. And as you can see, for the output waveform, when the clock is high and the load is high, this data register will register the data in the D into the Q, and when the load is high and when the clock is high and the load is low, this register will do nothing for the output, and when the clock is high and the load is high again, the register will again register the value in a D into the Q. So after verifying the output waveform, you can come back to the schematic here and click File, create symbol or current file, and write the name and click Save. After saving the symbol, you can come to the symbol tool and type in the name you just saved, and you can get the block for the 4-bit register.